Hello and welcome to Mr. Linford's math course. In today's video, we're going to be discussing the process of simplifying radical expressions. First, we're going to need to kind of define what is a radical expression and what are these concepts of roots and different types of nth roots. And then we're going to actually get into how to simplify them and break them down fully. Now, we're going to start with a place we know, and that is the idea of a square root. And what is a square root? Well, we're going to define it a little more abstractly than we're probably used to. A square root is going to be defined as b is a square root of a if b squared equals a. So this is the official definition of what it means to be a square root. If you want a number to be a square root of something, it has to be able to square to get you that number. We're not really dealing with any of this kind of square root symbol and notation. We're actually fully defining it in terms of the exponential value. Now, let's try to break this down a little bit. We know, for example, a very simple square root, and that is the square root of, let's say, 9. So I know that 3 is the square root of 9 because 3 squared equals 9. That is how I can officially prove something is a square root, okay? This symbol with the square root symbol here really doesn't mean anything. More so, it just implies this definition. So when we come to a problem where we have this symbol, and by the way, this symbol is called the radical symbol, or the radical sign, and the number on the inside is called the radicand. When we come across this situation where we see this radical symbol with a radicand, what it's implying is that you know what the a number is, but you're trying to figure out what number got you that. What number multiplied by itself got you that a? So we're trying to figure out what number squared gave us the number 4. So most of us would jump to the conclusion of saying, well, 2. 2 squared gets us 4, and we'd be correct. That is one of the correct answers. But keep in mind, there could be another value that when we square, we get 4. That value is -2. Remember, if you take a negative value and square it, you get a positive back. So in this case, we see that there are 2 answers to this problem. The square root of 4 is either positive or -2. These 2 possible solutions. Now, most cases, when you work with solutions, we oftentimes just work with the positive version of it. But it's important to remember that there are 2 possible solutions to these square root problems, both a positive and a negative version. Now, when we extend this idea beyond just square roots, we get nth roots. An nth root is going to be defined as b is an nth root of a if b to the n power is equal to a. In this case, we're no longer dealing with square roots. We're now extending it to any type of exponent, okay? Now we're going to say we're going to be able to take things to the 3rd power, to the 4th power, to the 5th, and so on. So for example, let's take a little example. Let's say, let me think. Let's try something like cubed. If I take the number 2 and I cube it, I raise it to the 3rd power, we get 8. So we could say 2 is the cube root of 8. We say it's the cube root of 8 because if we cube it, or if we raise it to the 3rd power, we get 8. Now, the notation is going to look a little different when we come across these types of problems. In this situation, let's stick with this example of 2 cubed equals 8. I would take the number 8 And if I wanted to imply that I want to find the cube root of it, if I want to figure out what cubed gets me 8, I would write this notation. And in this notation, it looks very similar to before. We have the radical sign, we have the radicand, except now we have this notation. This is called the index. And what the index does is it tells you what exponent are you working with, what type of root are you taking. Here it says, I want to find what was raised to the third power to get me 8. In other cases, I could figure out what was raised to the fourth power, or the fifth, or the sixth, or the seventh. Whatever that number is in the index, it tells you what the exponent was. Now, before, when we had the square root of 8, we didn't have anything written here. In fact, it was an imaginary 2. So the square root doesn't have anything written for the index. Its index is a 2. We just don't write it there. It's only for larger indices, like larger roots, that we write the index down. So anyways, when you see the third root of 8, we're asking what times itself 3 times got you 8? We could say that answer is 2. So this expression and this expression imply the same thing. Now, when you're taking different roots, whether they be square roots, cube roots, fourth roots, fifth roots, etc., we sometimes have what are called perfect indices or perfect roots. This is a situation where if you take the square root, the cube root, the fourth root, or whatever of a particular number, you're going to get a whole number back. So let's see some of those numbers, for example. In the first case, we could have the number 1, or 4, or 9, 16, 25, and 36, and 49, 81, 144, etc. All of those numbers are perfect squares, meaning if you take the square root of any of these numbers, you're going to get a whole number back. Those are really helpful, nice numbers to work with. Same thing that we have when we have cubes. There's certain numbers that when we take the cube root of them, we get a whole number back. The perfect cubes are 1, 8, 27, 64, and 125. That's a terrible 5. If you take the cube root of any of these numbers, you'll get a whole number back. And then the same thing for the fourths. Let's see if we can get those down. We have 1 to the fourth is just 1. 16. Let's see, that's 81. 4 to the fourth, I think that's 256. And 5 to the fourth, I believe that's 625. So any of these numbers, if you take the fourth root of them, you get whole numbers back. These are nice numbers to work with because they break down very nicely. We know that if a number isn't a perfect square, say for example, the square root of 5. 5 is not one of the perfect squares. 4 is, 9 is, but 5 isn't. If we were to try to evaluate the square root of 5, we would not get a whole number. We'd in fact get a decimal that goes on forever and ever and ever without repeating a pattern. Kind of like the number pi, because square roots are actually going to produce irrational numbers. So sometimes, very rarely, but sometimes, you'll get nice whole numbers as your answer. But a majority of the time, we'll have very long, complicated decimals. So let's actually get into trying to simplify these radical expressions. And we're going to need to first kind of figure out what does it mean to be simplified, and we're going to need to learn a technique for how we're going to go about doing that. So let's first start with this technique. And it's going to be the main method that we're going to need to use to break down these radical expressions. This method is called the multiplication property of radicals. And it says that if you have a radicand that can be expressed as two values multiplied together, all right? Two values, A times B. That means that you can break the radical apart and take the root of each of those things individually and then multiply them together. This is saying that the root of the products is the same thing as the product of the roots, if that makes sense. The idea is that we can split up multiplication. We can take the square root of things individually, or the nth root of things individually. And we're going to use this idea when it comes to simplifying down radicals. I think it's important to define what we mean by a simplified radical. How can we break down a radical completely? Let's use an example problem to see how we might want to construct that definition. So here is an example, the square root of 32. We should remind ourselves that we have this property, the nth root of a times b is equal to the nth root of a times the nth root of b. So this is the property that we're going to use. The idea is that if we can represent our radicand as a product of two values, we can split that radical up. But unfortunately, in this case, we don't have two things for our radicand. We just have the number 32. How can you rewrite this problem to apply this property and begin breaking down the square root of 32? What I'd like you to do is pause the video for a couple minutes, give this a try, really try to think about what this is saying. If you can rewrite the radicand as the product of two things multiplied together, you can split it apart. See how you can use that to help you simplify the square root of 32. All right, well, hopefully you had some time to work through this problem. There are a couple methods to going about and simplifying this. The first method we'll talk about, I'll call this method 1, is a little more obvious of a technique, and I think some of you might have been able to figure this part out. Let's take the square root of 32, and let's rewrite that root to be the square root of two things multiplied together that get us 32. So let's think of two factors of 32, two things that multiplied together to get us that number. I'm thinking of, let's say 16 and 2, for example. 16 times 2. Okay, I have a radical where I have two things multiplied together. Given this property, I can split that apart into the square root of 16 times the square root of 2. Now, why is this helpful? Well, take a look here. The square root of 16, I can evaluate that. I can get an actual number for that. That's 4. Now, the square root of 2, I can't get a number for that, right? That's just a decimal that goes on forever and ever and ever. I can't actually simplify that down. But I can simplify the square root of 16. And that's okay. We don't expect to get a whole number back. Look at the square root of 32. That's not a perfect square. 25 is, 36 is, but 32 isn't. Type it in your calculator. You're not going to get a perfect whole number for the square root of 32. In fact, you're going to get a decimal that goes on forever and ever and ever. In fact, that decimal is going to be 5.656854249, etc. So we don't expect there to be a nice value. We expect there to always be some component of a radical that we can't break down. And that's okay. We're not trying to get a whole number for this. We're just trying to get a simplified answer. Now, let's take a look at this problem again, but from a different starting point. What if instead of breaking 32 up into 16 and 2, you instead broke it up into 4 and 8. Because those two numbers multiplied together to get us 32. Well, you could apply the same rule, and this time you'd get 2 times the square root of 8. Well, that doesn't look the same as 4 and root 2. So I'm confused. What's going on here? We didn't really get the same answer, and that seems kind of like a problem. If we're going to come up with a method, it should always work, right? No matter what we pick as our starting point. Well, take a closer look. The square root of 8. Could we simplify that down any more? The square root of 2 couldn't be simplified, but could the square root of 8? Well, hopefully your answer is yes, actually. In fact, let's try to do that. The square root of 8 can be broken down into the square root of 4 times the square root of 2. And we know that the square root of 4 is 2. Square root of 2 doesn't simplify, and what do you know? We get the same answer as before. So we get 4 root 2 and 4 root 2. No matter where we started, we end up with the same answer. It's just sometimes we need to keep breaking down the radicals. So I think this is a good point to define what we mean by simplifying a radical. What does it mean to have a radical in its most simplified form? And maybe we should define it as when the radical, or when the radicand, I should say, no longer has perfect square factors. When the radicand no longer has perfect square or perfect root factors. In this problem, we're dealing with square roots. Obviously, in other problems, you'll be dealing with cube roots, fourth roots, fifth roots, whatever. So we want to make sure there are no longer any perfect roots that we can factor out from the radicand, okay? We want to make sure that it's broken down fully. Now, keeping this in mind, there's another technique that we could have used to simplify this. This is a very common method for going about and breaking down radicals. However, there's another method we should go over that is really going to be helpful, especially when we start to work with variable terms. So let me clear some space here, and let's do this next method. I'm going to change up colors. Let's try this in green. So we'll call this method 2. Okay, method 2 starts by saying take the number 32, just like before, and we're going to break this down, but this time we're going to break it down into its prime factors. Remember back in elementary school when you made prime factor trees? That was called prime factor decomposition. You broke down a number into all of its prime factors. So let's do that. Let's do that again right here. We broke 32 down into 2 times 2 times 2 times 2 times 2. So we can say that the square root of 32 is the same thing as the square root of 2 times 2 times 2 times 2 times 2. Okay, so instead of having 2 things multiplied together, now we seem to have 5 things multiplied together. I wonder how this might help us out. Well, actually, if we're careful with it, we're going to try to group together and break some of the radicals apart so that we group together pairs of the same number. So the idea here is I can group together 2 2s, another pair of 2s, and one's just going to be by itself. That's okay. We expect that to happen. And we might say, well, what's the point of this? Well, if you notice, we're forcing there to be perfect squares. And so what do we get? 2 times 2 times the square root of 2, which is 4 root 2. There is our final answer. This method is the method that uses prime factor decomposition. Rather than trying to, in our heads, come up with 2 factors of 32, and then trying to break those down further and further, we can go ahead and break it down completely using the prime factors. We get the prime factors, we group them together as pairs, and we break it down fully. We break them down each one by one. This method works every time, and it's a great technique to know, especially for when we get to much more complex problems. So if we were to write down a process for this, we would really want to say, 1, rewrite the radicand as the product of prime factors. Then for step 2, we're going to want to group the like factors as radicals. I'm using the symbol for shorthand. And let me clear some space over here. Once we have them grouped, once we have the like radicals grouped, we're going to just say to simplify the radicals fully. So a little note to ourselves here. Things like the square root of 2 times 2 is 2. So this technique, helpful to understand, very helpful to really be good at, because we're going to really kind of rely on this and need it for when we get to much more complex problems. Now, let's take a minute to practice a couple practice problems. What I'd like you to do is go through these 3 problems, try both methods out. See how you feel comfortable with one or the other. A lot of people tend to prefer method 1, which is fine. I use method 1 a lot too, but you really want to make sure you're also able to do method 2. So, give them both a try, see what you think, and when we come back, we'll check our answers. All right, well, hopefully you had some time to work through these problems, but you can take a look and check over your answers. We have 2 times the square root of 2, 4 times root 3, and 5 times root 2. You'll see that I tried a couple different versions. For the first problem I did method 1, and for the other 2 I did method 2. It's good to just get some practice with them and see which ones you're struggling with and which you could use some more work on. Now let's try to incorporate when we have variable terms. Here we have x to the 5th to the 4th root. So first we have to wrap our heads around what does it mean to be x to the 5th, and what does it mean to take the 4th root of this? So we're trying to figure out, kind of a little side note here, what raised to the 4th power got us x to the 5th? It's kind of a strange concept. So why don't we first begin by using the same, because we're going to have to use the multiplication property of radicals. Why don't we use the same idea of trying to break down the radicand? Before we did with numbers, now let's go ahead and try to do that, but this time with variables. Well, you might remember back when we worked with exponents that x to the 5th is x times x times x times x times x. That's expanded form, okay? And what we're trying to say is we want to take the 4th root of all of this. Well, if we go back before, remember when we were taking the square root of things, we made pairs of 2? Because we said when you make a pair of 2, that's pretty much what the square root's asking for. What times itself got you that? Let's try to do that here, but this time instead of making pairs of 2, let's make pairs of 4. We're being asked to essentially try to construct a situation where we're going to be able to take the fourth root of something. So let's try to organize and group together 4 of the x's. So let's see what happens in that case. We're going to split this up so that we have 1, 2, 3, 4 x's in one, and only one by itself. Well, how does this help us? This is the fourth root of x to the fourth. And if you think about that, the fourth root of x to the fourth, these just cancel out. That's just x. The fourth root of x to the fourth is just x. So this is why we want to group things together based on the index. The index is going to tell us how many to group of the like terms or the like values together. So our answer is going to be x times the fourth root of x. This is the thing that's going to give us x to the fifth. So let's write a little side note to ourselves here. An important idea that we really need to get down is that we want to make groups. We want to make groups of like values based on the index. Since we're taking a fourth root, we want to have a group of 4. If we were to take a cube root, we would want groups of 3. So that way the cube root cancels out with the third exponent, like we saw the fourth root canceling out with the fourth exponent here. Now, some students have asked me before, kind of, how does this answer show this relationship? Well, if you plug it in and give it a very careful try, working with the exponents, we'll see that if you raise this to the fourth power, that means we apply the 4 to each of these. So we have x to the fourth, and then we have the fourth root of x to the fourth power. Well, that's just x to the fourth, and the fourth root of x to the fourth is x to the first. So altogether that makes x to the fifth. So in fact, it does show that this works. It's just, since it's not a perfect root, right, we still have this radical as part of our answer. Since it's not a perfect root, it's not going to appear super obvious to us at first. Now let's try to piece numbers and variables together and simplify down something like 18x cubed. Do me a favor, pause the video for a couple minutes, try this technique out. Remember, the big idea is that when it comes to products in the radicand, when you have multiplication going on, you can split that up and you can take the root of each of the things individually. You can work with it separately. So use that idea and try to simplify this problem. All right, well, hopefully you were able to come up with something, but the first central idea that we have to work with when simplifying this problem is working with the number and the variable separately. Because we can split that up. We can first have the square root of 18 and then work with the square root of x cubed. We can do that separately. So let's break down the square root of 18. We can use method 1 for this. That's the square root of 9 times 2, which is the square root of 9 times the square root of 2. And the square root of 9 breaks down into 3 root 2. Now x cubed, let's see, that's the square root of x times x times x. We're going to make a pair of x's, so we end up with the square root of x times x. And then we have 1x by itself, that's okay. So we get the square root of x squared and 1x by itself. The square root of x squared is just x. And the square root of x doesn't break down. Again, that's totally fine. Now, we have 2 separate answers here. We have split up the radical at the beginning, and we found the answers for each portion. Now, let's put them back together. So we kind of worked in this direction first to break up the radical. Now let's work backwards to piece them back together. We have 3 times the square root of 2 times x times the square root of x. Using the associative property, let's rearrange this multiplication. So we have 3 times x times root 2 times root x. Well, if I'm multiplying the radicals, and if they're the same root, right, they're both square roots in this case, I can piece them back together. So let's do that. I get 3x and the square root of 2x. They both go back together under one radical. Please make sure to write your answer in this form. We want to make sure that we piece together the radicals again. And I can't tell you how many times I see students that when they get this, they would write something like maybe 3, they piece together the 2x, and then for some reason they leave this x on the outside. That's really, first off, it's kind of a poor notation, and it's very difficult for me to read because a lot of times students with their writing would write something like 2x and then they write an x here, or it'd be partially covered, and I'm wondering, is this a part of the radical? Is it not? I don't really know what you're doing with that. So we want to be careful with our notation. Anything that's not underneath the radical should be on the left-hand side. We should always include it on that outer side. And just, it makes it much nicer to see. And especially later on as we work with things that are called like radicals and we start combining radical expressions together, having this concise notation will be helpful. All right, now let's take a look at a problem that tries to incorporate multiple steps, right? We're going to have to essentially simplify a rational expression here. We're trying to break down this fraction and simplify it. But within the fraction is a root. That's going to also need to be simplified down. So why don't we do that first? Let's simplify the root on our own. So let's go over here, get some scrap work, and let's break down what is the cube root of 250. Okay. Well, I think method 2 is going to be helpful here because method 1, I don't know factors of 250 that are perfect cubes. At least I can't think of them off the top of my head. So I'm going to break down 250. 250, let's break that down into 2 and 125. Let's break that down into 5 and 25. And that can break down into 5 and 5. So the cube root of 250 is really the cube root of 2 times 5 times 5 times 5. We're dealing with a cube root here. So that means I need to make groups of 3 like terms, or 3 like values. And I have these 3 5s here. So let's take the cube root of 2. That doesn't have anything to go with it, which is fine. It'll just be that extra piece we can't break down. And let's group together these 3 5s. So you could go ahead and actually multiply those 5s together. You get the cube root of 125 and the cube root of 2. But a lot of times you'll start noticing we don't need to do this step. When you have the cube root of 5 cubed, you can just say the answer is right away going to be 5. So you can go ahead and do this step if you want, but you could also go ahead and skip it because we know that the cube root of 5 cubed, these cubes are just going to cancel out and we're going to be left with 5. So our answer for the radical is 5 times the cube root of 2. Now keep in mind, we haven't finished the problem yet. We just figured out what that radical is. So let's plug it in. Instead of having the cube root of 250, let's sub in 5 and the cube root of 2. So we need to go ahead and simplify down this radical. Well, let's see. We can combine the numerators. We can multiply these values to get 10 times the cube root of 2 over 30. And 10 over 30 can be simplified. We can get that to be 1/3. So we have the cube root of 2 over 3 as our final answer. Now, a lot of people have asked me, Linford, you're just dealing with the numbers on the outside of the radical sign. What about 2 here? Can I divide 2 and 30? Can I multiply 2 and 10 to get 20? Keep in mind, and this is a very common mistake, keep in mind that this, or I should say this, is not the number 2. We are not working with the value of 2 here. That's the cube root of 2, okay? That's a decimal that goes on forever and ever and ever and never repeats. That's not 2. So don't get confused with that and try to work with it. The thing is, when you have radicals, you really can't work with them. Because, again, they go on forever and ever and ever, never repeat a pattern. It's not really a number that you can multiply by and divide with, okay? Again, we'll see later on in the unit how to actually multiply and divide with these things, but it's not going to help you simplify anything down. So yes, when we simplify this, we're working with things on the outside. It's things on the outside of the radical that combine. Similar to before, in our previous problem, things on the inside of the radical combine together, while things on the outside of the radical combine together. So that's an important idea to understand. Things on the outside combine together, while things on the inside combine together. So now let's take a look at a problem where before we had to simplify a fraction expression that contained a radical. Now we're trying to simplify a radical that contains a fraction. So what can we do in this case? A lot of times students look at this problem and they jump into, okay, let's split up the numerator and the denominator. And let's try to simplify that down. You could do that, and you would get a correct answer, but it would be kind of messy. And there's some techniques that we're going to learn later on in the unit that you don't know about just yet that make this a little bit more difficult of a problem to solve. The big thing, and this is a little foreshadowing for later in the unit, we don't want radicals in the denominator. And I'll explain more in another video about why that's the case and how we get around that. But instead, let's try to think about how we can approach this situation where we can go ahead and simplify it down. It sometimes helps to work with the innermost expression first. In the previous problem, the innermost expression, the first thing we had to contend with, was the radical, right? Now, in this problem, the innermost expression is the fraction. That's the first thing that we'd contend with. That's the first thing that we have to do before we can cube root anything. Well, we have q to the 11 over q to the 5th. That can simplify down to be q to the 6th. So we take the cube root of q to the 6th power. So right away, we've gotten rid of the fraction by just simply dividing, working with exponents, right? So now, let's write q in expanded form. And we're taking this to the from the 3rd power, so we're cubing it. So if we're going to cube it, that means we need to make pairs of 3 common values. Well, we have that here, so let's see. Let's take the cube root of, well, we got 3 q's, and then we have the cube root of another 3 q's. Perfect. We actually got 2 pairs, two of the same valued groups. So that's going to be the cube root of q cubed and the cube root of q cubed. I'm wondering why I picked this variable, but okay. That's a tongue twister to say. So the cube root of q cubed is just going to be q. And the cube root of q cubed over here is just going to be q. So our final answer is q squared. All right, if you can get past all the tongue twisters, hopefully that problem makes sense. Notice that as we go through it, again, we're just making the groups that we need to, all determined by the index. Since this was a cubed problem, we made groups of 3. And then we just broke them down. We forced it to be a perfect square. So take a minute. Why don't we practice these problems here and see how you're coming along with them. So in the first one, we have 6 times the square root of 50. In the second problem, we have the cube root of 125. That's p cubed times q to the 4th. In the third problem, we're actually taking the 4th root of 4h over 64h to the 5th power. That's the 5th power there. And then in the fourth problem, we have 10 times the cube root of 81 over 12. So pause the video, take a couple minutes, practice these problems, and we come back and we'll see how we do. All right, well, hopefully you had some time to work through these problems, and hopefully they were able to make sense, but here are the solutions. We have 30 times the square root of 2. We have 5pq times the cube root of q. We have 1 over 2h, and then we have 5 times the cube root of 3 over 2. If any of these problems don't make sense, if you get any of them wrong, I'd try to pause the video again, go back through, see where you made your mistakes. And if you're unable to find them or if they're not making sense, I'd pause the video, shoot me an email. Let me know how you're coming along with the problems, show me your work, and let me see if I can help you find any of your mistakes. My email again is klinford@wccnet.edu. That's KLINFORD@wccnet.edu. Let me know what you thought of the video, or if you have any questions or comments, feel free to let me know. Also, feel free to leave any questions or comments down below in the comment section, and let me know what you think. Otherwise, take care.